Okay, this morning actually I was trying to convince you that using some mathematics, we can actually have a, an intuitive picture of what proton is all about actually. Okay, that was the, that was the conclusion that we had, that, we can express proton in terms of entities called quarks, mathematical entities called quarks, and mathematical entities called antiquarks. Quarks are basically certain representations of a group, and then antiquarks are basically certain conjugate representation of a group, and so on and so forth. Okay, so now we'll have to really see whether this is really the picture that we want to buy, or we are going to find something else. Okay, for that we need to do certain experiments. Okay, without experiments we don't get anything actually, because physics is driven by the experiments. Okay, let's look at, maybe I can start from here. Let us look at an experiment where you, scatter a proton with some object that we are 100% sure of actually. Okay, the particle that we are very sure of, we have understood quite a lot of it, is actually electron. Okay, electron, we know it's a point-like object as far as experiments are concerned. Okay, and we are going to use this electron as a probe to study proton actually. So this simple experimental setup that I call is an elastic scattering. You just bombard a proton with electrons, a bunch of electrons. And I want to study how it responds, and from the response I want to see whether the proton has quarks and antiquarks, or quarks alone, or anything else actually. Okay, that's this. Okay, so this, of course, we are not going to actually get anything out of it as far as the structure of this proton in terms of quarks, but we'll get something other than that actually, interestingly. So process looks something like this. You have a proton, okay, I call by this double line. Okay, something is happening. This is an electron. Let's say the momentum is Pe. This is another electron which is scattered off, Pe prime. Okay, this is the direction of the momenta. This is P, and this is P prime. Okay, and this is direction of this, and then this, because it's elastic scattering, it goes to same proton with the momentum P prime. This is a typical, scattering Feynman diagram for the scattering of this kind actually. Okay, I wanted to look at what this experiment is going to tell. Okay, so differential cross section for this, you can actually write down. I'll not put the arguments here, but to be transparent when you write down the expression for it. It's proportional to the flux of incoming particle. Okay, so it's for electron it is 2e, for proton it's 2m, because I'm considering these two, proton at rest, the electron is actually coming with some finite velocity and hitting it actually. So this part is called the flux. Okay, for those who are not familiar, it's just writing down explicitly. And this is the matrix element square. This is this amplitude for the process. You square it and sum up all those that we are not interested to, we keep it. In the sense, I'll send unpolarized electrons to hit on this proton. So I'll have to average or the polarization of the initial leptons. Then I'm also keeping this proton unpolarized, prepare the state which is not polarized, because this meeting is about polarized proton and the structure of polarized proton. But for this specific case, I'm considering the proton to be unpolarized. So the state that I prepared has equal number of positively polarized as well as negatively polarized protons, unpolarized. So I need to actually sum all the polarizations and average. So this bar actually means I'm doing this exercise of summing and averaging. Similarly, I will have to look at the final states. What I'm going to do with that actually, that is called phase space. So this is the amplitude for the amplitude square with all possible averages, and this part is called the phase space. Okay. Phase space is the part which takes care of all the kinematic configurations that we can actually have at the final state, and what we are going to actually look at. I mean, whether we are going to sum them up or we have to keep some of them fixed and then some rest of them and things like that is contained in this part actually. Okay, and m is the mass of the proton here actually. So the amplitude for this process, in if you use simple quantum field theory, you can write down very easily actually. Okay, I'm going to assume that this proton is a point-like actually. Proton is point-like because this is just an approximation that I make, first approximation. Okay, if I assume this, then any textbook will tell you, or any field theory book will tell you, this is something like this actually, this amplitude for this process is square times u bar of P prime gamma nu u of P. This is for the proton. It's just the product of two currents actually, which, okay. So this part, I'm sorry, yeah. So this part is for the upper part of the diagram. This is the part which is, for the lower part of the diagrams. So I put index nu here and mu here, and I assume that this photon that couples these two, particles, lepton and this proton, they couple electromagnetically. So there is a gamma mu here. I'm not considering any other weak interactions and things like that. In principle, you can have a W exchange or a Z exchange or whatever. Depending on that, you'll have a different React action. Okay, for a first order approximation, you can keep this actually. So the average over, this is for polarization of the initial leptons and the polarization for the proton actually, because proton is a spin of particles. That's the, so it will be proportional to 4 q power 4, just the squaring it, and the square of this is just a trace of this quantity actually. So P prime plus m gamma nu P plus m gamma nu prime, because I'm squaring it. So correspondingly, you will have a term for this actually. That will be square of, again, trace of this capital P plus m gamma mu capital P slash plus capital M gamma mu prime. Okay, these are the two traces that you need to evaluate, because we have actually averaged all the polarization of the incoming states. Okay, so far so good. Okay, so now given this and the phase space, I should be able to calculate the cross section. Okay, this scalar products are, I mean, the trace is easy to evaluate. Okay, you can find lots and lots of identities in the textbooks. Okay, this will be something like this. Okay, I'm writing down explicitly for some simple reason. This is P prime. This two dot products plus some cross terms. Minus m square. You might have noticed that I have dropped the electron mass, because I assume this is indeed true, okay, about 1,000 times or a couple of thousand times, smaller. So for all practical purposes, I can actually ignore that mass. Okay. So, and we also have this, I did not write what Q was actually. The Q is simply this momentum flowing here, which is PE minus PE prime. So, and this Q is PE minus PE prime. Okay. Now you substitute this expression here, it simplifies a lot, and it also gives you a very nice expression that you'll see, you'll keep seeing it actually. And in fact, it helped quite a lot of people to really cook up models actually. Okay, that is why I'm writing this expression. Not because I want to write some algebra on the board. Okay, so something like this, plus half of m square q square. So this is just substituting this, momentum conservation. So there is a momentum conservation that you can take p plus q equal to p prime. Okay, that is what I've written here, because this q coming here, then it added with this p will give you this p prime. So at every vertex there is a momentum conservation. Okay, if I just simply use that, you can actually get rid of this p prime and express everything in terms of the incoming and outgoing lepton momenta and the proton momentum actually. Okay, so this is something that we can actually have for this matrix element. Now the phase space part, okay, is simply this, because it's a two particle final state. So you have two phase space meshes. Okay, one is actually dqp prime of this. These are two invariant zeroth component of this. This is for the lepton. This is for the proton, which is okay. And then you have a so this is how the phase space looks like actually. So for this lepton, you have a dqp prime, and for this proton, we have a dqp prime. There are two such invariant, meshes, and then you have a overall energy momentum conserving delta function actually. So all I need to actually to plug in here and then get the cross section. It's as simple as this. Okay. Now I can do a simple manipulation, because this is an invariant phase space. You can write it as a d4p prime divided by 2 pi all power 4, 2 pi into delta p prime square minus m square into theta of p prime 0. This is very straightforward to show, because if you just integrate the time component of this or energy component of this, you'll get back this with Jacobian of this kind 1 over 2 p prime 0. So this will really help you to integrate this. So if I can actually substitute here, this integral actually I can perform very easily. Okay, so delta function you can get rid of it actually. Okay, that is one advantage of doing this. Okay, let's do, rest of the things are little involved. So let's now choose certain kinematics so that this integral can be performed. Otherwise, you cannot simply do an integration over this complicated looking dot products. Okay, so simple kinematics, we work in the rest frame of the proton. It's also called lab frame. Okay, if you do this, then you can parameterize, like proton is more like this p, and then p equal to e comma 0 comma 0 comma e. Very simple parameterization. And then p e prime is actually e prime comma e prime sine theta lab, comma 0, p prime cos theta L lab. Okay, I'm choosing this PE along Z direction, and then the scattered lepton is actually making an angle theta L, along Z axis with an angle theta L. Okay, it's a very elementary parameterization that everybody can actually work with. Okay, lab. It's also convenient. Okay, in this frame, you can work out this Q square, which is P minus P prime whole square. In the massless limit, it is just P dot P prime. Okay, this is minus 2 E prime 1 minus cos theta L. 1 minus cos theta L, I can write it as sine square theta L by 2. Okay, this is how this Q square, this invariant mass that it get exchanged is given by this actually. So this is as simple as this. Now what about this delta function that I mentioned in the beginning? Yeah, this delta function. Okay, let's look at this delta function actually. Rather, I will put line here. Okay, let's see what this delta function gives you. So p prime square minus m square is what is coming from the delta function. So that's nothing but 0. Okay. So what is p prime? P prime is equal to p plus q whole square minus m square. So it's easy to work out. P square equal to m square because all these particles are unshelled. It will cancel. So it is q square plus 2p dot q equal to 0. Is that what you could? So now q square I just now worked out actually. So it is minus 4e prime sine square theta L by 2 plus 2p dot q. What is 2p dot q? 2 into p dot q is actually 2 into m into q is e minus e prime. Okay, in the rest frame. Because this rest frame has an advantage of, sort of killing all those terms other than the energy part actually. Okay, so it's p dot q takes a very simple form actually, just m times difference of the energies. So I substitute here, it is 2m times e minus e prime. Okay, we're done. So we just substitute in this equation. If you substitute, you can make some simplifications because you collect e and e prime. Okay. So this gives you 0 equal to 2m into a into where equal to 1 plus 2e by m sine square theta L by 2. Okay. So I've just pulled out e and from these two terms in such a way that you can factor this overall factor 2ma, where a is equal to this and the remaining term. So the delta function contains now delta. So this basically implies you get a delta p prime square minus m square is simply 1 by 2ma. Both m and a are positive, so I don't need to put modulus, times delta of e prime y minus e by a. Okay. So as you can see that you can easily perform this integral because this delta function is only integral, it gives you this energy part actually, e prime. So if I want to do e prime integral, you can straight away do this e prime integral. Okay. Or you can also express the same thing. There's another representation which is delta q square plus 2p dot q. Okay, by pulling out this 1 by 2m from here, you can write it as nu plus q square by 2m, where nu is equal to p dot q. Okay, so there are two ways you can express this delta functions. So this way, we can actually do this energy integration and also this integration over the leptons. So let me just now continue with this and then write down the entire phase space now. So entire phase space now would look like something like ds2 equal to, I have performed one integral already. So you get, if I collect all the pi's, you get 1 by 4 pi square and d cube p prime to p prime 0. This is energy part. 1 by 2 am or ma delta E minus E by E. So this is my phase space. And this one I can also simplify further and write it as Te prime E prime square d omega divided by 2E prime. So this just goes away. So it is just E by 2 dE prime d omega. So this part is also very simple. So you get a very simple looking phase space for this particular process. So it is like E prime by 2 dE prime d omega 1 by 2 times ma times delta E prime minus E by A. A contains the angular dependency. Okay. So either I have this or I have this delta function 1 by 2m into delta nu plus q square by 2m. Either this or that. Okay. Any one of them. Or okay, it's not product of these two. Okay. So it's as simple as that actually. So now, now that I have set up a particular frame choice, actually, I need to calculate my matrix element in that frame because I need to consistently calculate both matrix element and the phase space in the same frame. So let's do that actually. So that's straightforward because all I need to actually plug in all the dot products computed in this frame. Okay. So it turns out there is this e power 4, q power 4. I'll keep q power 4 as it is, even though it's angular dependent now. Okay. So minus 1 by 2 q square. Okay, so maybe I'll just write down the expression separately. So now if you look at this, this part, P minus P, which is m times E minus E prime. So that is the part minus q square by 2 m into E minus E prime. That is the first part. And then you have a 2m square into E prime. I'll tell you exactly what I'm doing of m square q square. Okay, so let's look at this term by term. So this part is actually p times p minus p prime. Okay, in the rest frame, this is m times e minus e prime. It's as simple as this. Similarly, this part is actually m times e and m times e prime. So it is m square times e and e prime because you are working in the rest frame. So there is a lot of simplification because of the choice of frame actually. That's why I stopped here and proceeded. Okay, so this is what I have substituted there actually, those two terms. Okay, very good. So this is minus q square by 2 m into e minus e prime. This also can be read off directly from, let's say, one of the expressions here actually. What is that? M into e minus e prime. Okay, this one actually. This one is actually 2m into e minus e prime. This equal to 0, left hand side. So it is simply minus 4e prime times sine square theta by 2. Okay, so I can directly substitute here actually, q square sine square theta by 2. Okay, that's one thing. So by just substituting these two quantities, these two invariants, you get very simple looking expressions. So for that, let me also do a little bit of algebra. I pull out 2m square into e minus e prime. Okay, the second term here. So I can do that. If I pull out this term becomes 1. This term becomes minus q square by 2 m into e minus e prime divided by, this becomes 4, this becomes m square e prime, so m cancels. So this is what you get this for the second term, plus half of m square q square 1 by 2m square e prime. Okay. So this is simply sine square theta L by 2, this part, because you substitute q square contains sine square theta L by 2, and then everything cancels, so it's 1 minus cos sine square, it becomes cos square. Okay, so all I did is actually this simplification of this. So 8 into e power 4, q power 4, this becomes 1 minus sine square theta L by 2 plus q square by m, 2m square into sine square theta L by 2. Okay. So this is simply cos square. So it takes a very good looking form, like cos square theta L by 2. I think it's minus actually here. Minus q square by 2m square sine square theta L by 2. So this is how your matrix element looks like. So it has a part which is proportional to cos square, the part. This is simply because of the fact that proton is spin-off particle. You have all this dot products that are present, and those dot products bring you this angular dependency. Okay, so now I have a phase space part here ready, and I have this matrix element square ready, and then there is an overall flux factor. So put everything in this expression. Okay, if you are not clear about this step, we can do it during the tutorial or whatever, whenever we get time. So it's very straightforward. I've just used these two identities. Identity number 1, identity number 2. This is only two identities I just used to arrive at that actually. This everything expressed in terms of this angular integration. Okay. Any questions so far? Nothing. Okay, good. So I'll put everything back actually to the original expression, and you get the following term. So if I substitute everything and then bring this t prime d omega to the left, what you will get is actually 4 times alpha square times e prime square times q power 4 into cos square theta L by 2 minus q square by 2m square into sine square theta L by 2. Okay, where alpha is the fine structure constant defined by u square by 4 pi. So all I did was actually I substituted this expression for the matrix element square and phase space part. I forgot to add one more term. Sorry about it. So the last part is actually delta nu plus q square by 2a. Okay. Either I can have this delta function as a function of nu and q square by 2m, or I can equivalently have this delta function, okay, where I can still perform this integral over E prime, electron energy. So either I can have this, this delta function or this delta function, whichever I like. Okay, but it doesn't matter because I'm interested in the angular distribution. So this distribution, this cross section for, cross section for this elastic EP scattering, where I look at the energy and angular distribution of the scattered electron is given by this actually. And you can see unpleasant delta function sitting here actually. Okay, so your cross section is actually, I don't think it's not continuous or anything. It just means that actually only this condition is satisfied, you have a non-zero cross section. Okay, so it's proportional to this delta function. So it's called elastic electron proton scattering. Okay, what is the use of all this is actually, okay, suppose if electron happens to be point-like, and I do perform an experiment with this, then I find the distribution exactly identical to this, okay, and I can fit the coefficient of cos square and sin square, it turns out to be exactly this, then I can bet everybody that, proton is point-like, okay, that's the statement that you can make. Otherwise, you cannot make such a statement. Okay, so I assumed something that proton is point-like. I assumed it. This proton interacts with electron electromagnetically, and I assumed that I can use whatever quantum field theory that I know to compute this quantity. I get this actually. Okay, now I will give it to an experimentalist and say that okay, please confirm this. Okay. He will do an experiment, or he or she will do an experiment, let's say angular distribution. So look at how it depends on cos square or theta L or energy, okay? And you can actually fit the coefficients of these two quantities, sin square and cos square, if the experiment is precise, okay? If the numbers agree, then you can bet, okay, proton is point-like. If not, it is not. Okay, that's why this exercise is very important. You don't do this, very straightforward textbooky exercise, you won't be able to make any statements about proton. Experimentalists, of course, can measure elastic cross section. You'll get a number actually. That number could be some few pico bonds, or femto bonds, or auto bonds, or whatever, depending on the kind of energy the range that they look at. They can also nicely plot, how it looks like and things like that. Okay, if we want really to make statements, we need to really have a formula of this kind with your own assumptions and then proceed actually. Okay, everything is clear? Okay, now let us look at what happens if I not assume that proton is point-like, but it has some structure. Okay, but I don't know what structure I can assume, because if I assume structure, then I'll have to modify the interaction actually. The interaction that how electron interacts with the proton. Okay, and I have to make my own, wisdom. Okay, and to make assumptions and then write down. Okay, once this attempt was made actually. Okay, and see. Let's see. I'll also show some plots later on. Okay, suppose it is not, proton is not point-like. What will happen to this formula actually? Okay, I'll have to again repeat entire exercise. If I have a computer and I have programmed everything, I can do it actually. Okay, it's not very difficult. Okay, I don't think when you grow up, you will sitting and doing all these calculations by hand. There are many tools to do this, but it's good to do at least once in a lifetime to do things by hand, because you get a lot of insights. Okay, so with that spirit, actually, let me continue. So the proton, okay, P prime gamma mu p is what, this is what I wrote down actually for this part of the okay, the way proton couples to this by a point like way this way with IE gamma mu. That's why the second term contained U bar IE gamma mu U. Okay. This was the amplitude for a point like proton interacting with the photon. Okay. If it is not point like, if it has some complicated looking structure, which I don't know what it is, okay, then I cannot write this simple looking formula. However, if I assume that this interaction is electromagnetic, it preserves certain symmetries, then I can actually write down the most general vertex, okay, in some limit, okay, in the limit that, proton is a point like, it will just, go back to this expression. That's the whole idea actually. So how do I write down an, most general current that is responsible for this interaction actually, okay? Hiding all the ignorance in that actually. Okay, so the way to do is actually, it is the simplest way of doing. Okay, there are many ways you can do it. You replace this gamma mu by a bunch of terms. Okay. Okay, this is the most elegant way of modifying this vertex. Okay, let me explain what it means actually here. So I replace this gamma mu by a couple of terms. One is proportional to gamma mu itself, okay, with a coefficient some f1. Another one, which is also allowed by for the same Lorentz property, because this is a Lorentz vector. So you can write down a Lorentz vector in a theory where your fermions and photons interact. Okay, so Dirac theory allows to construct a term of this kind using gamma matrices. So sigma, I forgot to put what sigma is actually. Sigma mu nu is half of gamma nu commutator. Okay, so using this Dirac gamma matrices, you can actually couple of gamma matrices. You can construct this. Okay, you can ask, can I add more and more terms and then make it more and more general? Of course, you can add more and more terms, but you'll have to check whether all the symmetries that strong interaction respects or electromagnetic interaction respects in this case are all preserved. You cannot add some terms which containing gamma phi or epsilon mu nu and things like that, because each one come with their own whatever properties. Some of them can violate parity, some of them can violate time reversal, some of them can violate Lorentz invariance, and so on and so forth. So you have to make sure that what you write down here is sensible, consistent with the symmetries of the theory. So, and what are these F's? F's are not known. In the sense, when I use my wisdom to write down a most general expression, of course the most general expression will have ignorance hidden in it actually. Okay, those ignorance are actually parameterized by these two coefficients f1 and f2, which usually are called form factors. These are called form factors. For the reasons that obvious from the name itself actually. Because if it is not a point like, it has got certain form in whatever structure, and that we call it as f1 and f2. And why it's function of q square? You can ask why not actually, because if I assume it is independent of q square, that I'm making an assumption actually. So I'll have to let it have a dependency based on what they appear here actually. So this is a current where you have a p and p prime. So what are the invariants that you can construct? You can construct invariants which are combinations of this p square, p prime square, and p dot p prime. Okay, p square and p prime square are proportional to mass. So you can have p square, p prime square, and p dot p prime. So all of them boil down to some m square, and some q square. Okay, p dot p prime is just p prime you can write in terms of p dot q, right? P dot p prime is p plus q. This is m square plus p dot q. Okay, again p dot q you can write in terms of delta function. This is nu is p dot q in terms of q square. So all of them are related. So there's only one invariant that you can write because m square anyway is constant for this. So form factor having m square dependency is okay, it's fine. It's not a big deal. Okay, so I dropped m square dependency and kept only q square dependency. So it comes simply from the fact that you're looking at this vertex. There's nothing else. Okay, fine. So these are the form factors and the dependencies are understood. Now, if I again start doing this algebra and back, I think you all leave it, the auditorium. So I'll not do that. So it's your exercise to actually repeat this. Okay, we did an exercise with gamma mu. Okay, and did not consider this so far. Just adding this, repeating this is not going to make a lot of work for you actually. So you can do that exercise. Okay, now if I substitute that current, okay, back into my matrix element square, okay, here, every the remaining part of the board will remain as it is because kinematics is not changed by changing the relaxing the approximation that proton is a point like. Okay, kinematics remains same, energy remains same, momentum remains same, everything remains same. Only thing that it's going to change is this matrix element. Okay, and that is easy to work out. Okay, and I again if you substitute back, you get a result which is just the modification of your earlier result. Okay, how it is going to modify? Because I cannot cross beyond this point. Okay, I'll write down the answer here. So this modification would look like d square sigma by dE prime d omega equal to 4 alpha square d square e prime square q power 4. So it changes only the coefficients of these two quantities actually. Okay, because of the simple looking Dirac structure, the structure of gamma mu's and sigma mu and gamma mu, all it does is it changes. How it changes? It changes to this. Let me write down this f1 square minus kappa square q square by 4m square f2 square cos square theta l by 2 minus q square by 2m square f1 plus okay, so you can see that the coefficients are modified actually. Again, go back to the experiment list. Ask them to perform this experiment. They've already done it actually, let's say. Now you fit it, okay? Now look at, extract this F1 and F2 from the experiment, from let's say angular distribution, okay? And if you see it's, F2 is 0 and F1 is 1, then you can bet its proton is point-like. And if they measure F2 and F1 as a function of Q square, it indicates that proton is not point-like, it has some structure. It has got some non-trivial structure. Structure depends on the energy that you pump in to the system. Okay, change the energy, you will see you can probe the structure through this function actually by changing the. So you can get a profile of how this F looks like as a function of Q square. That tells you this, the structure of the proton as a function. So if you actually, if you're very interested, you can actually, this is in momentum space, it's function of q square, okay? Now if you want to have a visualization of this function in real space, what do you have to do? What do you have to do? Sorry? Fourier transform this actually. So you'll have to somehow appropriately Fourier transform this actually. You can also, Fourier transform your current and see actually. Put it back and reconstruct your current in the, position space, whether it looks like a vector current or an actual vector current or how it looks like. So you can actually have a picture of, the proton, real picture of a proton. It's like, really like a scanning, putting a proton inside a, some microscope and look at the structure actually. So it's the experiment is like a, scanning experiment actually. You can really scan the proton and see it has any spatial structure in it actually. Okay, so like that, you can, in this case actually this, there's a name for these things, F1 and F2, and this kappa is called the magnetic moment, because if you study Dirac theory in detail, actually you will see that you get a non-zero magnetic moment because of the interactions, okay, and also because the electron is a spin-off particle, okay, and it is called anomalous because it's coming from the quantum effect, okay. So this is called anomalous magnetic moment, and these form factors correspond to this electric form factor and magnetic form factor. There are better way of expressing them actually, okay. It's not this quantity that one is most frequently used. So I'll just write down another one actually, which you can use it for studies. Okay, so now the more familiar ones and also have a direct consequence with the understanding of the proton is this combination actually. They're called electric and magnetic form factors. You take a combination of these two. This is just a combination, some name you give actually. There's nothing very complicated physics behind it actually. You make a combination of F1 and F2 in this case. F1 plus kappa F2, okay. Then what is usually used in the study is this, the same result expressed in terms of GE and GM. So just for the completeness, I'm actually writing down this expression for you. Q power 4 G square plus tau GM square divided by 1 plus tau cos square theta L by 2 minus Q square by 2M is changed 2 tau into G M square sine square theta L by 2 delta nu minus Q square by 2M, where tau is actually minus Q square by M square. So what people study, not just that combination F1 and F2, they study this GM and GM. One can extract GM and G and GM, okay, and then it is supposed to give you, the picture of hadron in terms of magnetic structure and electric structure and magnetic structure of the proton. So I have a couple of slides that I wanted to show. So this is something that we should actually take it very seriously, that proton is no longer point-like. It has got structure, and the structure can be understood by just using basic principles actually. That assume that proton is spin-off particle, and it interacts with electron through electromagnetic interaction. These are two assumptions that I have made, and I parameterized the interaction vertex or the current that is responsible for this scattering in terms of two unknown functions f1 and f2, equivalently in terms of g1 and g2, ge and gm. The entire cross section can be now expressed in terms of two unknown functions, ge and gm, and these two unknown functions, which contain all my ignorance about proton, is actually parameterized, hidden there. By measuring this cross section, comparing against this expression, you can actually get the form of these two form factors, ge and gm, as a function of q square. And that will tell you, whether it peaks at some value of q square, or it smoothly falls up with q square, or it increases with q square. A priori, I don't know anything about it actually. This function could be sine of q square, cos of q square, or exponential of q square, polylog of q square. I don't know. Okay, only experimentalist can tell us how the function looks like, and is it going to give it some more hints, because we are in search of, or we are in sort of in the process of checking whether what Kalman and Zweig said is correct or not. Actually, the proton is not still now we have not made that conclusion. Actually, we have only found that it has some structures. Okay, so let me just show you the picture of this form factor, how it looks like, because that's real physics. Okay, if it is point-like, it will be just a delta function. Let's I don't know who is. There's no new interpretation. It's just, if I give you A and B, you can write some combinations of it. But this is directly related to electric and magnetic moments by some reason, actually. Maybe some of my experimental colleagues can tell. This is conventionally measured quantities, actually. You can measure F1 and F2 also. If you measure these two quantities, suppose I measure this, I can extract Ge and Gm. Usually what is used is this, actually. And this is for some conventional reasons, actually. But you need two functions to actually characterize your proton, to understand the structure of the proton. Okay, that's the point. You can take it, actually. Can you just show me some? So in the remaining 5 minutes, I will just show you so something is missing here. So basically, I just described how to get this formula. Okay, and as you can see that if it is a point like, the coefficient of cos square and sin square will be, whatever I have shaded, the portion will be 1, 1. Okay, it just means this normalization that I have written down here, and it's related to the magnetic moment through this formula. Okay, and if kappa is 0, that's what Dirac predicted, actually, right? The Dirac tree level magnetic moment is just E by 2m. Okay, and we know there are quantum corrections. I have not calculated any quantum corrections, but all the quantum effects are actually embedded in this kappa. If electron is point-like, okay, I can measure them, or in the theory I can compute, actually. This is what you do in your first year undergraduate course or during PhD. It's not undergraduate course. So you calculate what is this, corrections to this. We call it anomalous magnetic moment, G minus 2 or whatever, in some normalization. Okay. So similarly for the neutron also we can get some number. Okay, so typically the experiment would look like this. Actually, you have a rest, the proton at rest, electron beam hits. E naught is, in my case, is E. Okay, its target is a hydrogen atom which contains unpolarized. Okay, and then the angle that I have defined theta L is this theta L in this frame. And you have this actually, somehow that sine square theta is taken out, I think. Okay, if you take out sine square theta out, you can write down this cross section as some mod scattering times this. This is a fancier way of writing actually, it doesn't matter how you write it. But at the end of the day, that the coefficients are the ones that matters. Okay, the measurements, as you can see, these are something much before even your parents were born, 1965. Okay, so this is the nucleon form factor Q square as a function of Q square. Three of them are given actually, GEP and GMP and GMN. E for electric, M for magnetic, P for proton, N for neutron. Okay, normalized by some numbers, typical values, and this is how it looks like. So as you can see, it's not constant with respect to Q square. It changes with Q square. Okay, as you increase Q square, if you collide it with very large energies, then you can see that the size of G, starts becoming smaller and smaller actually, as you can see from the plot. Okay, so this shape is very important to understand actually. Okay, now you cannot compute, however, we can actually parameterize actually. You can make a fit, and the fit looks something like this actually. It's a very famous fit. Electric form factor GE looks like 1 by 1 plus Q square by 0.71. And in fact, you can use this actually to do Fourier transformation to get some spatial picture of this. This is at the energy around 10 GeV square. This is out. Sorry? N for the neutron actually. P for the proton. So you can perform same experiment by replacing proton by neutron. You can get. So I mean if you can do with the proton, you can also do it with the neutron and also understand, whether the neutron is a point-like or it has got a structure. Wonderful. So I'll stop here. Okay. Now my next topic will be to sort of probe more actually. Right now I was very mild with proton actually. I don't want to disturb too much. I used what they call, elastic scattering, and I really want to know what it is. I'll have to do more violent things to proton, and in the process I might get more information actually. This violent thing that I'm going to do goes by the name deep inelastic scattering. You'll see that by pumping in huge amount of energy, I'll break the proton if possible. And if it really breaks, it is going to give you a better picture of what proton is all about. Right now, I got some picture. Okay, so that's my next talk actually. So I'll stop here. Your questions, please.